Okay, let's jump right into this explainer. We're looking at the invisible magic keeping interactive audio running flawlessly on our phones. You know that feeling when you're completely immersed in an app and the spatial sound is just dialing you in perfectly? Yeah, that doesn't just happen by magic. It takes some serious, hardcore engineering to pull that off on a device sitting in your pocket without completely torching the battery.
But to start, we really got to ask ourselves a very practical question. Why does mobile game audio sometimes just glitch out? Like you're deep in an AR experience or a heavy mobile game and suddenly, click, pop, lag. The illusion is instantly shattered. It's incredibly frustrating, right?
Well, that brings us to our grounding research for today. It's a 2026 study from the Journal of Resource Management and Decision Engineering by Habibi, Mir Mahadi, and Jalili. They thoroughly dissected this exact audio degradation problem and came up with a genuinely ingenious architectural fix.
Let's hit Section 1, the mobile audio bottleneck.
So here are the stakes. As we push further into the audio metaverse, interactive sound isn't just a fun extra feature anymore, it is the core of the experience. But we're fighting some severe hardware constraints. We're talking limited CPU and GPU power, operating systems that aggressively throttle performance to save your battery life, and super unpredictable thread scheduling. Throw all those together, and you inevitably get massive latency and jitter when trying to process complex spatial audio. It's kind of like trying to sprint through mud.
And that brings us to Section 2, the two-thread architecture.
Here is exactly how the researchers solved that bottleneck. It's a strict architectural breakthrough where they split the engine into two completely isolated domains. Think of the audio thread as a high-speed express lane. Absolutely no stopping allowed. No input/output operations, no memory allocation, period. Just strict real-time processing. Meanwhile, the control thread is your regular highway. It handles all the messy logistics like loading files from the network and running the UI logic.
So how do they talk to each other without causing a giant traffic jam? The control thread fires off commands, things like play or change pitch, through ultra-lightweight, lock-free message queues. The audio thread just swoops by and grabs these instructions in quick batches. It's a remarkably elegant way to pass notes without ever forcing that express lane to hit the brakes.
Moving on to Section 3, optimizing the digital signal.
Now we look at how engineers push that audio thread express lane to its absolute limits using some very clever digital signal processing, or DSP tricks. They calculate audio in grouped blocks of frames rather than one sample at a time. They pre-calculate complex math curves into lookup tables, and they swap out massive convolution models for lightweight Schroeder reverbs. It's all about having the answers ready ahead of time to totally bypass heavy, repetitive math.
And check this out. D-normal numbers. These are microscopic, lingering decimal values. Think of them like the very end of a fading echo. Believe it or not, these tiny numbers can literally crash a CPU or cause giant slowdowns, because the processor just chokes trying to calculate them. To fix it, engineers actually have to write code to intentionally flush these tiny decimals directly down to zero.
Beyond that, they dive deep into low-level optimization. They pack the data arrays perfectly into memory, using a structure of arrays setup, and they exploit parallel processing capabilities, specifically SIMD, like Neon on ARM devices. This lets the processor crunch multiple audio samples in the exact same fraction of a second. It's literally wringing out every single drop of efficiency from the hardware.
Okay, let's jump to Section 4, managing voices and resources.
So everything we just talked about is great in a vacuum. But out in the wild, what happens if a user triggers an overwhelming number of sounds all at once and completely maxes out the mobile device? That's where the engine executes a tactic called voice stealing. It sounds dramatic, but it's brilliant. It ruthlessly prioritizes sounds based on importance. A distant wind noise? Sacrificed. Cut off instantly so that your super important UI button-click sound can play without stuttering. This case study data maps it out perfectly, showing exactly how the system degrades gracefully. Look at the low load profile. 4 to 8 voices, negligible latency. Medium load handles 16 to 24 voices completely fine, but watch what happens as we hit the 32+ high load tier. Instead of crashing the whole app, the engine dynamically scales back audio quality and aggressively steals voices. It sacrifices a tiny bit of background realism for complete application stability.
Which brings us to our final part, Section 5, Building the Interface.
Even with this absolute beast of a real-time audio engine, developers still have to wrap it in clean, modern user interfaces that won't accidentally ruin everything by adding CPU strain. Taking the NetMusic 3D setup as an example, they lean on Redux to seamlessly manage and share the internal UI state. They use Tailwind to rapidly style the app without writing bloated CSS files. And they utilize Iconify for rich, scalable SVG icons that stay incredibly lightweight. The entire goal is keeping the non-real-time domain just as lean as the real-time audio domain.
So, wrapping up this explainer, it leaves us with a pretty massive thought. As our immersive digital demands just endlessly grow and we transition fully into the audio metaverse, will brute force mobile hardware ever truly catch up? Or is brilliant architectural design always going to be our ultimate savior? Either way, next time you're gaming on your phone, take a second to appreciate the absolute, invisible magic happening right inside your pocket.